Hey. So we could go through one of these again since we have quite a bit of time, or I could just do a brand new one here.
Can we do a new one?
Yeah, sure. I guess I just did inelastic, so let's do inelastic now. Wait, I don't need to share. Okay, let's look at an inelastic one. So local native couple. Okay, so we got an inelastic one here, and let's use two pucks. Usually, well, whatever. Okay, we're gonna have two, like, let's write the problem. Let's say this. Sometimes you see this. I'm not sure if he'll use it, but that's kind of the hint that it's inelastic, because they stick together at the end. Looks like he's just telling you inelastic, which is fine. But two sticky pucks, we can say that actually. Inelastic collision. Let's do one where they move towards each other. That's what they. Oh, I wanted to ask you. These problems on the worksheets and stuff, are the ones on the quizzes like exactly the same, pretty much, or do they? Do you have to do extra math, or is it pretty much the same?
It's usually very similar.
Okay. So let's not have them move toward each other. This is okay. Move in the same direction. And then so I'm just being a little redundant, but inelastic collision, that's the point. Move in the same direction, then stick together after contact. Elastic, they bounce right off. They do not stick together. Kinetic energy is conserved in that case. It is not in this case, inelastic. Okay, puck one. So they are, puck one has mass, 5. Okay, and if P1 is moving, we'll answer all of the questions. So what is so you see this, and you say inelastic collision. And okay, so we're gonna say this, and this should. We say the momentum is conserved of the system. Let's see if the couples go. Right. And so we want the velocity of the final velocity of the system, because remember they're sticking together, of the system. So after they connect, there's no puck one and puck two. You treat them as the same. Let's draw the situation. Initially, we got a puck. We got another one. This one's moving. Oh, yeah, sorry, this is stationary. So that one's not moving. Puck 1 is not. Sorry. Come on, man, I gotta focus. All right, so puck 1, puck 2, this is not moving. There's no velocity here. V equals 0. Sitting on the track, I didn't really make that clear, but this one is initially not moving and this one is moving in the beginning. That's the initial situation. The final one, like we just said, we say inelastic collision means they stick together. Oh, okay. They're stuck together. They are one mass. Okay. You know, both pucks or something to say, just drive it home for yourself. This is the initial momentum. Pi, the initial momentum of the total system, Pf. So what are these things, right? Well, Pi, what is it? It's the momentum of the first puck plus the momentum of the second puck. That's what we say, the momentum of the system. Okay, what is that? Well, it's the momentum of the first puck. What is that? M1 times V1. P equals MV. M1 V1 plus 0. Yeah.
Mm-hmm.
Because the puck is sitting there, no momentum, no velocity, no momentum.
Yes.
Cool. Final momentum. Well, it's P equals MV. What's the mass here for the final situation? What is M? What's the mass of both the pucks? Because it's one object. That's really important here. So it's, M total, but let's be very explicit here, M1 plus M2. And then, well, final velocity of this thing, this thing that is both pucks put together.
Wait, what?
Wait, what? What is that? Are you there?
Oh, yes.
Hey, sorry, did you say something?
No, it was just cutting out. I got a little confused.
Oh, sorry. Okay. Yeah, I'm not sure if it's me, probably me. Okay. Clear so far?
Yes.
Okay. So the initial momentum, well, we want to say momentum is conserved.
Okay.
So momentum is conserved. So the initial momentum, what is it? Well, it's M1, V1 equals M1 plus M2 times this final velocity of the thing. Why? Because I've just substituted here, right?
Mm-hmm.
And then we can say, well, let's solve for VF. Well, I solve for it, I isolate it. That means I have to divide by whatever is not VF, since that's what's there. Okay, well, we have these values, right? We just need to plug it into the calculator and get the final velocity of this thing.
Mm-hmm.
Where's my calculator? There it is. Okay, so the first mass is 5 times, well, it's moving at 10, divided by the total mass of the thing, 11. 5 plus 6 is 11. So I got 4.55. Great. So, I think that's what I did before. So we just calculated this. This is the only way to find the velocity.
Mm-hmm.
And you're just saying momentum is conserved. Fine. Now you ask, this other thing they ask is, what is the initial momentum of the system, right? So you tell me in words, what's the initial momentum? Not equations yet. Tell me in words.
Okay.
I'll go back to the picture here.
The initial of both of them, or
What is the initial momentum of the system?
oh, okay. So
Just in words right now, just as simple as possible.
okay, so if the initial velocity in the first half would be well, puck 1 is 10 and puck 2 is 0.
Yes, yeah. But remember that momentum is mass times velocity.
Mass times velocity.
E equals
So,
mv.
oh, so
You're on the right track there. I just want to give you the clearest picture. Sorry to interrupt your thought process, but I don't. Because in words, like this is what conservation of momentum tells us. And you say, okay, great, but that doesn't help me. If I'm in your position right now, you're like, okay, great. I don't know what that means. But to understand what this means, you have to understand what that means.
Mhm.
That is the initial momentum of the system. Do those do those words I don't want to be condescending, like do those words make sense to you? Because they need to if you want to try to understand it. Because it's kind of a weird thing to say, but you really have to understand each, initial momentum, just that, and then of what? Of the system.
Mhm.
Are you good so far on that?
Can you explain it again? I'm a little confused.
Sure. So let's write it down. I think these words are good. I've learned that about you. More kind of a visual person, aren't you?
Mhm.
Okay. Let's see. Let me see something here, maybe so we can drive this home. This equation. Can I use shorthand EQ for equation?
Mhm.
And then of momentum. Then here we go. Yeah, okay. This is what, when you get a chance, you should try to do this when you're next time for physics, exactly what I'm doing here, what all these variables mean, and convince yourself.
Okay.
It's kind of like an on your own exercise, but it really helps. And so you write down this stuff and then literally write down the words. But then don't stop there. Make sure you show me or your instructor or somebody that knows what they're doing and say, is this correct? Okay.
Okay.
So then PI, it's a variable, just like all of them are. What does it mean? And then I want you to write down the words, what it means. The words are the initial momentum of the system. That's what that variable is. It's okay, especially when you're first learning, but even if you are pretty far in, it's okay if you don't understand, don't feel bad. The initial momentum of the system.
Mhm.
You say, okay, great. It still doesn't really tell me much. It's not really there, right? Let me just finish this real quick. And then well, PF, oh yeah, P is momentum. I have an F, that it's the same thing then. It is this, so I can copy it down. Oops. There. But it's not initial, it's final now, the final momentum of the system. And then you have to take it a step further, right? You hopefully kind of see the hierarchy here. This is the biggest thing. This is what you spend weeks on. Oh, equation, conservation of momentum. Great, easy. But what does it mean? It means this. But then you have to go again and say, what does that mean? And you have to identify each of these things. Initial momentum. Well, hopefully you know what momentum is. It's P equals mv. Don't ever forget that one, right?
Yeah.
But now initial. Well, okay, I have an initial situation and a final situation. Go back to your problem 1 on the worksheet, just for an example, but you can do this for anything and all the problems we've been working on. You got a car and a truck traveling. Boom, that's the initial situation. Truck, car. What happens? Well, the truck hit the car. Okay, so there's a velocity, fine. I don't really care what the number is, but there's some velocity here. The truck hit the car. I don't know how fast the truck is moving, but now I know the car is moving at a different velocity. Hence,
Yeah.
we have a different value of this,
Mhm.
which is the final momentum of the system. So that's where that initial and kind of momentum comes from. But then if you're able to get there, that's great. But the real, whatever capstone key here is system.
Mhm.
Initial momentum of the system. You have an initial momentum of the car. Let me get it right here. Well, what is it? It's m times v. It's the mass of the car times velocity of the car in the initial situation. But the system is everything in the thing, which is the truck plus the car. That's why we write down PI, which is what? The initial momentum of the system, all of the momentum added together equals all the momentum added together.
Okay.
That is why we get the equation PI equals P, which is momentum. We're going to add all the momentum together, the momentum of the truck plus the momentum of the car plus whatever. I mean, in this case, it's just truck and car, but you add them all up, whatever they are. While keeping this equation in mind, because then that P truck, well, that's just the mass of the truck times the velocity of the truck.
Mm-hmm.
So if you understand this PI, the left side of that equation, and I mean, truly understand everything here that I have on the page, then this is the same exact situation, but now it's just for the right hand side.
Okay.
Is that a little bit clear? Is it how much like?
Yeah, that makes more sense.
Maybe driven home. I'm not sure. Some examples help for sure, but
yeah.
So if I go here, I literally just covered the paper with my hand to try and take that away. Idiot. Okay. Two sticky pucks, an elastic collision, move in the same direction. So you draw your picture. You get in there and you say, okay, these are two pucks, right?
Mm-hmm.
This means the initial momentum. I mean, this is the initial situation, but it's the momentum. That's what I care about. We represent it as PI because that equation is true, unless you lose energy to the ground or whatever. This is momentum conserved. You know that for sure because when it's inelastic, you can't use the kinetic energy equation. Okay, I'm getting too much. I want to try to be more basic. This is your situation. I mean, take a look at each piece here, what I have here. You know what I mean? Break it down. Like those things are together. The puck one's moving. There's no velocity for that one. But those things combined is the total system. That's why I get this equation. Back. And this is like your drawing board, maybe not that, but you say all the momentum added together. That's my initial, the initial momentum of the system. What is that in math? All the momentum added together. So normally it's this. We got two pucks. So I'll even be even better and say, oh, right, add all the momentum up. Oh, right, but P equals MV. Keep track of your subscripts. But then, but it's actually just that because that's 0. Hence, I have what I had before. Yeah? Okay. If you understand that, well, as long as you are careful with your picture and you understand all that good stuff, then you can say the same exact thing. The same principles apply. Oh, what's the final momentum? Well, let's go back. It's the final momentum of the system. What's all the momentum added together? What is the moment? How many objects do we have? Let's add up all their momenta. Well, it looks like we only have one object. Why? Because they're stuck together. And so we don't have two objects anymore. Kind of makes sense.
Yeah.
And so again, you say, oh, let's add up all the momenta. Well, momentum, let's add up each individual momentum. But like I just said, we just have one momentum because there's only one object. Well, P equals MV. We're using subscripts here, but the mass is M1 plus M2 because they're stuck together, right? So the mass of that little guy, that moving object, is both of those masses combined. Like imagine if they were just like Play-Doh or Play-Doh. You couldn't distinguish the two pucks. I know you can now, but that's the point, is that they're not two pucks anymore. Smash those Play-Doh balls together and you have one Play-Doh ball. Same mass as the two individuals, of course.
Yeah.
And then, well, there's our final momentum of the system. There's our initial momentum of the system. And now you end what you started with, which is this, the equation that governs it all. Definitely for inelastic collisions.
Yeah.
We call that thing, well, this is the equation for conservation of momentum, right? Come back here, there it is. So then you set it up and you say, oh, equation for conservation of momentum. And then of course, if I have it on the previous page, I just plug those in like I would normally. And then solve for that, because that's what we like to do. You know, that's what they're asking for, which is what usually they're always going to ask for. What's the final velocity of the thing, of the object that has been combined to form one object? And we solved. I mean, I just did it. You know, it's a calculation. I don't care what the number is. And then they want you to check if momentum is actually conserved. And you say, well, I don't know. Does this equation hold true? Let's check. What is PI? Use the same logic you did before. Well, it's just M1 times V1.
Okay.
Which is, 5 times 10.
Yeah. Okay.
Then they ask you to calculate the final momentum. Again, it's just this, which is, well, now this combined mass here is 11. 5 plus 6, those are the numbers there. Did I do that? Or did I do, wait, let me see. M1 times V1 is 5 times 10, 50, and then divided by 11. Okay, good, 4.54. Okay, and then so, it's 11 times, and then I rounded, so it's going to be a little off, but you should get the same one if we're doing conservation of momentum in the elastic ones. And yeah, I got 50.05, but I rounded. Remember, I round. This is actually 4.54 forever. So
yeah.
So then, indeed, in this situation, momentum is conserved. So I've gone through the process a couple times now, and that's really the most important thing. Like we said, the examples are important to understand it. So maybe just another example, just to try to drive this home, right? Okay. Yeah, and all of these, when you draw your pictures or think about it, it's all one direction, which is nice because momentum is a vector. Why? Because velocity is a vector. So you can have two-dimensional thing. And obviously, it's more complicated. Same principles though. So hopefully, it doesn't throw that at you. But he doesn't have objects coming at coming at one another, like moving towards one another, like this. They're all moving in the same direction, which is nice. So these things move in the same direction for now, but okay, it's hit from behind by a truck. So the truck is 25115. 3.2 meters per second. Great. Okay, we're going to assume elastic collision. So think about it. Tell me when you think you know what that means. In words is fine. Elastic collision.
Wait, define elastic collision.
Yeah, in words if you can.
An elastic collision is when they're coming from different directions and they hit each other and they come in contact, and then they bounce off each other without any like visible damage or deformation.
Nice. That's pretty damn good. If you didn't read that off of paper, that's pretty good. What's the equation? That's the most important thing now. What is true? What is conserved in an elastic collision?
What is conserved?
What's the math equation that you should write down? Remember, this is physics. You got to have the equation or you don't get anywhere, right?
The equation is Ki equals Kf.
What does that mean?
That means
In
the
words.
initial kinetic energy is equal to
Yes.
the final kinetic energy.
Perfect. Of the system, the initial kinetic energy of everything, not just one object, but the total system, everything in that picture. Okay.
Mhm.
We're going to answer this guy. So this is a key. When you see this one, just do it, because I would assume that's what he wants. When you see this phrase on your quiz, go ahead and jump right into the one you just said. 100% correct. Kinetic energies are equal. And you say, oh, initial final. What the hell does that mean again? And oh, yeah, I have to draw a picture. And this is the situation. That's what that kinetic energy is of the system at this point in time, the initial.
Mhm.
So car, truck, I'll try to make it longer. And 3.2 meters per second. 2 meters per second on the car. And then, oh, what happens? That's the initial situation. Is that crowded for you? Is that all right for you? Or do you want me to?
Yeah, it's okay.
Okay. I'm just repeat myself here. This is the initial situation. We have two objects. We want the kinetic energy of the system, not just the kinetic energy of the truck, not just the kinetic energy of the car, but what is the system? And so how do I do that? And if you go here, this is another thing I highly recommend you do. Like we did right here. I know it's a little crowded now, but you write down the thing and you say, what is it? Say what it is in words. It's better if he doesn't tell you, because then it means you have to think a little bit. And it's not too bad once you actually understand it. And oh, okay. And I'll give you a hint here. When you do your thing, it's going to be, it's going to be Ki. Okay, fine. What is that thing? The initial kinetic energy of the system, right?
Mhm.
Just remember those words and then try to understand them. I know you know, but really, and the important words here are initial. Well, what is that? Convince yourself. Kinetic energy, I think you're good on already. What is kinetic energy? Energy associated with motion. And then the equation is a good thing to know, but then the system, truly understand system. That's what I'm telling you. It's the everything. Add, and then you say add kinetic energy, all kinetic energy together.
Okay.
That's the equation. So Ki equals K1 I, right? The initial K2 I. If I have 100 objects, well, you're going to have 100 kinetic energies. You're not going to worry about that. So it's just 2 usually, but only in the initial atom together. Okay. Got in there. So it's so important, because if you understand that, then you're on the right track to know what to do, because now the final situation is the same thing. If you can get this point here and understand it, then you can get the rest of it.
Mhm.
It's moving at 2.85 at the end. And we don't know how fast the truck is moving here at the end, but imagine an elastic collision. Yes, kinetic energy is conserved, but look, the car is moving faster. So that means the truck has to be moving slower. There's no way for it to be moving faster for sure, or at the same speed, because there's no extra energy here. The initial is equal to the final. Look, it's moving at 3.2. Look, it's moving at 2. The car gets hit. Boom, what happens? It goes forward faster. So some of that energy of the truck is transferred to the car. Now, more importantly, what are these things here? The initial kinetic energy of the system. What is that? Well, I don't know. But I do know it's the initial kinetic energy of the system. Means I add the kinetic energies up. That means K of truck plus K of car. Where in the initial situation only right now. Why? Because that's what we're looking at. KI. So now I'm using the age-old equation that you know very well. But this is where you got to come in and go a little crazy with the subscripts. Otherwise, you're going to lose track of stuff. And I know it seems like, why is this? I promise you that this. I promise you that that thing is the exact same thing as that. I didn't even do it right. MT. Are you truly good with that?
Mhm.
These things are the exact same thing?
Yeah.
Okay, cool. Oopsies. And so that means I'm just adding kinetic energies here. Kinetic energy of the car. What's the equation for kinetic energy? Oh yeah, 1/2 mv squared. But I better be real careful with my subscripts because I got all these objects. I lose track of what I'm doing. Great, that's the initial kinetic energy, the energy of the system, which is the energy of the truck plus the energy of the car. Just kind of in this complicated form here. So like I said, if you understand up to this point, then you can get the rest because it's the same thing for KF. K truck final. In fact, let's even be, there we go. It's a little better. Normally you would do that. I just shouldn't neglect that. Car final. Okay, well, I did it here. I just have to do it again for the final situation. And that's why it's so powerful. I don't care what the numbers are. Just write the equation down first. You can deal with the numbers later. You've gotten that down. But now what's the final kinetic energy of the truck? I don't know. What's kinetic energy again? Oh yeah, 1/2 mv squared. So 1/2 m mass of the truck. That's hence the T. I don't need a prime because it doesn't change, but I will use a prime here to denote final. I mean, just look at, let's try not doing that if that's a little confusing. But look at this VT squared thing now. Well, I got a VT squared over here under my initial situation, but I already know my initial velocity is not the same as my final velocity. So hopefully that makes it a little more clear why we use this prime. Now, it's not it's not just to make it more confusing and so we don't know what the hell's going on more than usual, but it's to help us and guide us and say, oh, this is different. This is a different velocity. Kinetic energy of car, 1/2 mass of the car, V primed car, V primed final. Why? Because it's different than the initial, so I want to use a different notation. Okay, we're going now to finish and solve for what they want. You have to, this is where we started. Why? Elastic collision. Went through all this work. Now we go back there and the KI, let's write it down. Elastic collision, that's what this means. Well, what is KI? Well, we just wrote it down. So I'll write it down again, Great. That's what KI is for all the reasons I've been saying over and over and over. Final kinetic energy, we got that equation. Now we solve for the final, how fast will the truck travel after the collision? These are the questions on your thing. And so hopefully you're following along with your own work, tomorrow on the quiz, and like, okay, what do they want? They want the how fast the truck will travel. What is that? Oh, it's the final velocity of the truck. Oh yeah, use the prime or whatever notation you use. Sometimes you'll see TF. I don't know if that's what he's doing with no primed, but it just gets a little cumbersome at the subscripts.
Mhm.
So we'll solve for this thing just like you normally would. So solve, let's do this since it's a big boy. Solve for what V prime T. All the algebra is the same. Let's, okay, cancel 1/2. Or times it by 2. And if you, can you see that all the 1/2s go away?
Mhm.
Are you sure?
Yes.
Sides by 2. Okay. This is I'll be very clear. There's plus MC. Hooray for us. Now, what are we doing? Solve for VT. So now the next one is, well, we're getting VT by itself, so we're going to have to subtract this. And look, if we didn't put a prime here, look, we would get 0 there. We have to use different notation. We do get the 0 here, of course, but so then MT VT squared plus MC VC squared minus and then divide by MC squared. That part is pretty clear, right?
Mhm.
Get this by itself. Okay, good. And then we get this crazy guy. But just like all of it, it doesn't matter. Plug in numbers. I don't care how complicated it is, as long as you're keeping track of your variables, right? And you know what they mean, then it doesn't matter. MT, what is that? Mass of the truck. Oh, yeah, let me go back, I think did some weird ones. Okay, so 251.5 times what's the initial velocity of the truck? Notice my initial, I didn't use a prime for my initial, so that must mean initial. 2.2 squared plus the mass of the car, 132.5 times 4, 2 squared, minus 132.5 times the final velocity of the car, 2.85 squared. Great. Get a number, divide it by mass of the truck. I got a number. Square root that thing. So we get 2.84. That's the velocity. And you tell yourself, oh, that's the velocity of the truck. Right. Great. Awesome. That's this thing that we're looking at after the truck hit the thing. Now we know it's 2.84. But look, that's less than 3.2. But if you went through it before and understood what we were talking about, well, yeah, the car was going faster. That's obvious because they tell us that. And it's obvious when you write the picture down. Maybe it's not obvious right away if you don't have enough practice, but you look at it and you say, well, yeah, the car's moving faster. Okay. But guess what? Elastic collision means there's no change in kinetic energy. So that truck better be moving slower,
Mhm.
or else we screwed up.
Okay.
So then let's do this. Because now they want you to ask initial momentum of the system. And so we literally wrote that down. Just going to go be as explicit as possible here. They say, that's what's on your paper, your worksheet. It says, what was the initial momentum of the two vehicle system? the initial momentum of the system. Oh, PI, add the momentum together for PI or PF. But so let's go over here and say, oh yeah, momentum system, PI. Oh yeah, how do I do that? Add all momentum. Oh yeah, that's right. PI equals, okay, the P of the truck plus the P of the car, the momentum of the truck plus the momentum of the car. Oh yeah, but also momentum is M times V. Oh, okay, so then this is obviously the momentum MT, the mass of the truck, MT, times the velocity of the truck. What's the
Mhm.
car? That. This is the initial. This is all given information. So we got 132.5 times 2 plus 251.5 times 3.2. 1069.8. Nice. Now, the final momentum of the system. Say prime if you want, since we've been using that notation. Just know that it's different than the initial momentum. The sum is the same because conservation momentum. We should get the same here. Oh yeah, elastic. Well, we have to see. Let's see. So, oh yeah, different velocity. So it's the final. So let's use our prime. And it's the final. So let's use our prime. We just calculated that in the car. So the momentum of the truck, oh yeah, it's moving. That's what we calculated. That's the truck, 2.84. Okay, so the thing of the car is 132.5 times the final velocity of the car is 2.85, which they give us, plus the mass of the truck, 251.5 times the final velocity of the truck is this.
Mhm.
Where'd it go? So in this case, we see it is a little bit faster. Not faster, that's not, the momentum is a little more. See,
Mhm.
last time it was a little less. I did round that 1, 2, but it shouldn't be that far off. So like I was saying before, in elastic, it might not be conserved every single time if you lose energy to the ground. Not much, obviously, right?
Mhm.
But yeah, maybe I didn't. Did I do, what did I do? 2.85, that's what I was supposed to do. And then, yeah, 2.84. Let me check that velocity again real quick. But if there's any, so yeah, let me know if you have any questions while I double check this other calculation. 2 squared. Oh, I actually don't think I squared that. 4, okay, that thing's squared. I think I got a different number. So the mass of the truck is 255.15. Oh no, I guess not. Guess it's good. Okay, 2.84. That's fine. Oh, I did do it on the wrong one. I put the 2 point. God, this guy's got to be so careful. I said this was 2.84, but it's not. This one is 2.84 because we're
Oh.
solving for the velocity of the truck in the end. I mean, this is pretty much the exact same as what you. Yeah, truck. Okay, so let me try that again. So it's not gonna be 1091, but it will be the momentum. The final momentum of the truck is the mass of the truck. 251 times. We got 2.84 on this one. Should be a little closer, and was surprised it wasn't conserved before, but let's check. It might work out this time. 132.5 times, and its final is 2.85, and the final answer. Oh, I did do it right. Okay. Well, some energy is gained. There's something a little weird here, but I mean, these principles are sound. I'm making a mistake somewhere, obviously. Because if anything, the momentum should be lower at the end if it's not going to be conserved because it's lost, right? But it shouldn't be more. But hopefully the point is clear on how to go about this, because this is the elastic one.
Mhm.
And I mean, it's pretty involved, obviously. So yeah. Any questions?
I don't think so.
Okay. Let's see. Oh, that's about it. Okay, well, yeah, if you got, there's only a couple minutes left, so if you want to just get off a little early, or you want to ask a question, either way, or I can
I
go
think
through a
I'm
few
good.
things. Okay, good.
I think I'm good. Thank you.
Awesome. Well, good luck tomorrow. And
Thank
yeah,
you.
all right. Have a good night.